In this presentation, I will lead you to go through the whole process of my final project, which aims to analyze the classification algorithms on KDD Cup 99 dataset using R Hadoop. This is the outline. My presentation will be composed of these four big parts. First, I will give a brief introduction of the task and the dataset I applied during the whole analysis process. Then, I will introduce the data pre-processing I have done on the datasets. After the data pre-processing introduction, I will give detailed explanation of the main work, the model build, their performance with or without the feature engineering, and finally, I will give a short summary of my work in this project. First, I will introduce the tasks about this project. In this project, we supposed to build a network intrusion detection system, a predictive model capable of distinguishing between bad connections called intrusions or attacks and good connection that is just normal connection. For the good connections, they are just labeled as normal, while for the bad connections, they are labeled with the specific attack types, such as Smurf or guessing password. Although tens of specific attack types exist, they all fall into four large categories: denial of service, that is DOS, remote to user, R2L, user to root, U2L, and probing. For example, Smurf is in the DOS, that is DOS category, while guessing password belongs to the R2L category. And this subtype table here gives the category belonging for the specific attack types existing in the training dataset. For the dataset content specifically, each line of the dataset represents an instance of the KDD Cup 99 dataset, which is a connection that includes a sequence of TCP packets starting and ending at some well-defined times, between which data flows to and from a source IP address to a target IP address under some well-defined protocol. Without the discrete information included, an instance is represented in the training and testing dataset as a line of data with 41 features and one label, which indicates whether the connection is normal or an attack with exactly one specific attack type. Important to know here is first, test data is not from the same probability distribution as training data, which is also known as dataset sheet, simulating the real-world simulation on the situation. From this table, we can find that the distributions of the instance are different from training and testing dataset. Specifically, in the testing dataset, about 5% of the instances are of R2L category, while vary in the training dataset. Correspondingly, the training dataset have 5% more instances of DOS category comparing with the testing dataset. After searching the online information carefully and discussing with the professionals in the machine learning fields, there is no recognized solution for this situation so far, and this is one of the difficulties in data mining. That this is one of the reasons leading to inaccuracy of the models. The second problem is the test data set includes specific attack types which do not exist in the training data and are the variants of non-attacks existing in the training data set. Specifically, the training data sets contain a total of 21 training attack types with an additional 17 types in the test data only, occupying almost half of all the specific attack types. This leads to an incompatible problem in my initial analysis in which the models cannot by any means make a valid prediction over the new classes since they have never seen these classes before. Yes, after doing cross-validation on the test dataset with the correct label giving, I got all the 38 specific attack types and obtained the categories they should be classified into according to the information provided by this website, this below website. The classification table is as shown here. The black ones are from training dataset and the red ones are from the testing dataset. And this is the method I can think about to classify them. Before we go into the details of the model chosen, I need to introduce the dataset I have used so far. The first pair is the original KDD cup 10% dataset as training data and a test data code correct with the correct labels disclosed after the computation. This pair of datasets are the source of the other two pairs, which are both 1/4 of this pair of originally obtained datasets. The second pair of datasets is the KDD two-label training and test, in which I pre-processed all the attack to abnormal, while the normal just stay unchanged. In this case, the incompatible problem caused by the novel attack types in the test dataset is no longer a problem, and I used this pair of datasets to build my baseline. The third and final pair of dataset is the KDD5 label training and test, in which I keep only the normal label and the four labels, each representing one categories of the four. In this case, the incompatible problem has also been resolved. Moreover, the different classification performance between the categories of attacks will be distinguished in this way. Okay, then I will introduce one important thing, that is the pre-processing of the data. As I have introduced before, I have pre-processed the data into the two versions, 2 labels and 5 labels, in order to eliminate the incompatible issue. Except this, I also did two types of pre-processing on the dataset. First, I did normalize the features as shown using this piece of R code. In this way, all the data should be in the range of 0 to 1 in the ratio to their minimum and maximum values, that is their range, eliminating the previously existing bias. Secondly, I also did my feature engineering. After built the baseline with the normalized data, I analyzed the features in the datasets and found that the features are actually not equal to each other. Instead, several features are more informative than the rest, such as the protocol type, duration, and service, which should weigh more compared with the others. For example, longer duration time always indicates X-log attack, especially over hundreds, and Smurf attack are always coming with the ICMP protocol type. Since I used R package to build the models, and it's difficult to modify the built-in cost functions, which is the common way to leverage the weight of various features in machine learning, I employed a method I found online. That is, if the feature is in the symbolic value type, I added a duplicate for the feature with a different column title. And if the feature is in the continuous value type, that is their numbers, I added a column with the natural-based logarithm of their value with a different column title. In this way, these informative features should have more decisive effect on the final prediction. Okay, let's see the model build. After searching the information for this KDD cup dataset and trials on the dataset, I chose these 4 models to do the experiments, including KDD, jli3, Nevis, and random forest. And I will explain the reason why I chose these 4 in the later section. Except these 4, I also tried several others, including neural network and SVD, but they all run very slow and always crash halfway, so I cannot get result from these models and have to give up on them. For all of them, the output includes a confusion matrix and the corresponding statistics of the performance, such as accuracy and kappa value. Okay, first model, naive. The reason I chose naive is as reported that naive classifier performed better than some popular models on KDD Cup 99 dataset in predictive accuracy, such as SVM. Especially is better on the accuracy of detecting denial of service attacks. So I chose it as my first candidate model. The performance of the prediction is naive on the three pairs of datasets without the feature engineering are shown here, including the accuracy and the kappa value. We can see that the cross-validation on the test dataset owns the highest accuracy and best kappa value, which makes sense since I have described previously that the training and testing dataset own different label type distribution. I also included the confusion matrix for the 5-label dataset here. From the matrix, we can see that the most incorrectly classified type is least grade, which was classified as normal but actually is DOS attack. Based on the result of my analysis, the pre-processing that weighed more on the protocol type should help improve the classification on the DOS attack type. Okay, this page shows the result from the same model, same experiments, but with feature engineering. We can see that the performance improved with the feature engineering specifically as predicted before. We can see that the number in this specific grade decreased from around 8,000 to 3,300 under the same dataset. So we can see that the feature engineering worked very well. Next, let's see the second model I chose, that is KNN. Since the given dataset states that even the first order KNN can also do a good job on this dataset, I tried KNN. I first transformed all the symbolic features to integer using a transfer table described here. Since the KNN package in R can only deal with the continuous value, that is, it can only deal with number. Moreover, I only use 1/10 of all the available data to build model and test, since testing on lazy learner that is KNN is very, very slow compared with other models. And after trials of different case settings, we can see the accuracy without the feature engineering here. Then this is the performance with the feature engineering. Similar to Novice, the performance of the KNN was also improved with the feature engineering, since the performance of KNN, including accuracy, kappa value, and confusion matrix, which was not shown here because there are 4 of them, and I do not have time to explain. All of these statistics are very similar, so I decided now to give more explanation for it and save time for others. Okay, next on decision tree. From my investigation of the problem, several researchers used C4.5 and SC4.5, which are both extension of the traditional ID3 algorithm, and they obtained relatively good results. So I decided to give it a try. I found C4.5 is a built-in algorithm in R, which made my research easier. Similarly, I did my analysis on all 3 types of dataset. Their performance were shown here. From the confusion matrix for the 5-label dataset, we can find that the numbers in these 2 grades are relatively high compared with the other incorrectly classified grades. These 2 stand for the ones predicted as DOS and R2L on the remote to local attacks, which were actually normal connections. According to this phenomenon, I weighed more on the servers and the source type features, since they showed a high relevance with these two categories of attacks. Okay, with the feature engineering, the results were shown here. We can see that the red circle two types of errors were still more than others, but they have been decreased for about half. So the effect of feature engineering is good for this case. Okay, final one is random forest. I got bad performance from this model that is random forest in one of my previous assignments, one of my previous projects that I chose it as my last attempt. I tried several configurations for the numbers of trees for the random forest and found that tree number equal to 10 gives the best performance, and thus I decided to apply it here and show it result for the three types of data sets. From the performance, we can easily find that it also has a very high incorrectly classified grade. This grade represents the ones that are actually normal, but were predicted as DOS attack by the model. With the feature engineering, this number of instances in this red circled grid decreased about 2,000 from the previous 7,000 without the feature engineering, which is about 1/3 improvement. Although the effect was not so great as the other models, the feature engineering still helped to some extent in this case. Finally, summary. From this table, we can see that for both without or with feature engineering, KNN and the random forest have better performances. And the improvement with the feature engineering range from 5% to 8%, indicating that the feature engineering worked for this task. For the future work, if anyone can resolve the uneven attack category distribution problem, better performance might be able to be obtained, which should be hard. Okay, finally, thanks a lot for your time. If you have any question, please contact me through the email address shown in the red bottom corner of this page. Thanks.